Good morning, mathematicians. It's moving day live stream, but I shouldn't have hit the play button until I grabbed my coffee cup. Yeah, that's a problem. Okay, let's get stream set up and then I'll get a coffee cup. Actually, I should probably run and grab it now before people start trickling in. Yeah. Okay. Yeah, welcome to the Moving Day live stream. Oh, it says here I have 300 videos now. I thought this was going to be the 300th video. It's very interesting. Yesterday I went and edited a video. Good morning, Edit Smith. Good morning, Julie. Yesterday it said 299. It's definitely proven time, Boris. It said 299, and then I edited the thumbnail of a video, and then it said 300. Very suspicious. And I checked. I didn't accidentally publish that video, which is set to come out. Sorry, I guess you can't see that I was staring intently as I pushed down my French press. Nice, the audio is probably picking up that good. Which I might abandon, by the way. Apparently, coffee. You lose some of the health benefits if you drink it unfiltered. Apparently, filtered coffee is better. Can I explain something about the existence of fiber products in schemes? The proof seems very messy to you, using some horrible relative gluing. Oh, interesting. Which proof are you looking at? Are you looking at Hartshorn? AeroPress seems like a lot of work, though. Do I want to work that hard for my coffee? I mean, I guess the French press isn't zero work, but it almost is. Let's look at... yeah, because I'm just thinking... let's look it up. Maybe it's in Hartshorn. Fiber products. Is it spelled this way? In our proof and lecture, you think it was Hartshorn. Okay. It's faster than a French press. Oh. But it's one cup, right? It's much cleaner. Is it? I thought I remember using the AeroPress. My ex had an AeroPress, and I remember using it at her place. I didn't feel like it was that much easier. First properties of schemes. Okay, here we go. Fiber product. Yeah. Just usual definition of fiber product. For any two S schemes, a fiber product exists. You're late with this, but did I hear about the counterexample to integral Hodge conjecture for abelian varieties? No, I didn't. Okay. Well, we will come back to this. Don't you worry. But counter example to Hodge conjecture Didn't we... integral Hodge conjecture. Doesn't that... No, okay, I thought maybe that... See integral... a recent counterexample, Hodge conjecture, blah, blah, blah. Show me the preprint. Matroids and the integral Hodge conjecture? I don't know. I clicked on the more AI. Oh, is this the Reddit post for it? It seems like a different paper though. Proof of Hodge conjecture. Oh, for abelian. Okay, that's a different thing. Yeah, I guess maybe there aren't too many people discussing this yet. We proved that the cohomology class of any curve of a very general, principally polarized abelian variety of dimension at least 4 is a multiple of the minimal class. The same holds for intermediate Jacobian of a very general cubic threefold. This disproves the integral Hodge conjecture for abelian varieties and shows that very general cubic threefolds are not stably rational. Huh. There are 2 preprints, both with matroids. Wow. Wait a second. So what's the difference between integral Hodge conjecture and the rest of it? It's like Q coefficients instead of Z coefficients, or what's... X be a smooth complex manifold. Integral Hodge conjecture states that every integral Hodge cycle. I see. So it's basically just the Hodge conjecture with... Because Hodge is, what, like Q bar or something? Yeah, okay. Don't give me the motivic, blah, blah, blah. I want to know the original Hodge conjecture. C coefficients. No, yeah, it is. Yeah, it is Q coefficients, right? I see. Wow, that's very interesting. Thanks for mentioning it. Matthias, I mean, there's nothing that's too much to ask for office hours. There may be things that's too much for me to do. There may be things I don't feel like doing in office hours. Those are totally different things. But we're going to talk about Julie's question first. I'm going to talk about Julie's question first. But I'm going to read your problem anyways. In a factory, 100 units of product, 5 of which are defective. Oh, what is the probability that exactly one of them is defective? Yeah. Okay. Well, I mean, maybe that's easier to answer than Julie's. But let's okay. No, I'm gonna look at this first. Okay. 2 schemes. The fiber product exists. So as usual, we proceed locally. So by the way, yeah, the messy gluing argument. I guess this is something that one just has to get used to, because this is kind of, I mean, schemes are just glued affine schemes, so it's a pretty standard trick to just take, some affine cover and then glue it. Okay, so hopefully the first part is makes enough sense. Step 2 follows from the universal property unique up to isomorphism if exists. Step 3, gluing morphisms. Okay. We've already seen how to glue sheaves and how to glue schemes. Now we glue morphisms. Yeah. Maybe I should ask if there's a... This is a long argument, so maybe I should ask if there is a particular part. Well, we're almost through, actually. Yeah. Yeah, that's kind of the whole thing. Yeah, technical but reasonable. I would agree. Maybe you actually have to do the gluing schemes argument. Yeah, I mean, did you do exercise 2.12? Yeah. Or exercise 1.22. Those are probably worth doing. You just need to make sure that each of these 3 schemes in the pullback can be generalized from affine to arbitrary, right? Okay, good. Well, if you did 1.22, then yeah, then you're in good shape. 2.12. Wait, oh, I was looking at the wrong one. Yeah, here we go. Yeah. Yeah. Maybe you're hoping for too much, you know? Yeah, sometimes things just get technical. That's how it is. Okay, what's this problem of Matthias? It's a basic counting problem, so you know I'm gonna get it wrong. 100 things in the factory, 100 units at random. Pick 3 units from the units at random. What is the probability that exactly one of them is defective? Well, 100 units, 5 are defective. Well, I mean, how many ways are there to choose 3 objects? There's 100, choose 3. And by the end of which summary, yeah, right. Yeah. Yeah, so we have this is our total, and then I guess the easier thing would be to say how many ways. Well, we want exactly 1, right? We want exactly 1. So we could either pick so either it goes in I guess does the order doesn't matter though, which is confusing me a little bit. We pick the first one, like the defective one is either here, here, or here. Oh, sorry, here. And so I'm tempted to say it's something like, 5 times 95 times 94, and then divide by... no, we don't have to divide by 3. Yeah, terrible. My my combinatorics undergrad would be so disappointed in me. 14%? That kind of seems high, no? Because if you were to draw, like, you have only you have a 5% chance of drawing a defective one on your first go. Proof by computer enumeration. Yeah. Yeah. How many here have read Mathematical Science Fiction by Greg Egan? Wait, Greg Egan, for instance? You're asking about the general genre of mathematical science fiction, and you're saying Greg Egan is a writer of such a genre? I don't think I've ever read such a thing. Actually, I've read Anathem. That's absolutely right, Rod. 0% by proof by I tried and it didn't happen. Honestly, aiming to finish Heartshorn is a bit overkill, but feel comfortable with the first 3 chapters and move on. Yeah. That's true. Good morning, Rubik's. Yeah. I mean, if we look at a simplified version of the problem, let's look at a simplified version of the problem. I mean, imagine there was just, let's say there was 2 defective things, simplified as much as possible, out of a total of 4. And let's say we were drawing 2 things. So what are the total possibilities? Or let's say if it was 2 and 2, then there's just one possibility. We have to draw 2 defective things. There's no other way. Okay. What if it was 1 and 2? Well, then either we could choose, either we have no defective things, or we have, yeah. So hang on. I think I was right with. I think this is right. Because you have 1 defective thing. So how many ways are there to do that? Well, you have 1 choice, and then 2, and then that's it. Order doesn't. We don't. The order that you draw them in doesn't really matter. Or we have 1 way to choose. Yeah, each of these. Yeah, so I'm pretty sure it's this. It's 100 choose 3 over this. No, maybe we need to divide because of the lack of order, though. Maybe there should be a division by 2 here. I don't know. This is embarrassing. What's mathematical science fiction? Hilbert's formalism project succeeding. Wow. I would read. Yeah, imagine like the equivalent of lit erotica, but for mathematicians, where it's just like fantasy novels about Gödel's theorem being true, or like Hilbert's program succeeded, Galois won his duel, Hope Core stuff. You just joined. What's cooking today? What is cooking today? Hypergeometric distribution? What? A hypergeometric distribution? What the? You get it by 3 times 5 over 100 times... No, that doesn't sound right at all. Why are you dividing by 99? Why are you dividing 95 by 99? This probability question is called hypergeometric? Really? It's such an... it doesn't deserve that name. Hypergeometric. Hypergeometric distribution. Discrete probability, the k successes and n draws without replacement. Wait, so was I right? Yeah, the probability shouldn't it be like you choose n from 5 and m from 95? For all n plus m equals 3. Maybe. Right. Let's go. Where's the describes the probability of k successes. Right. So we would count it in this time. We could count it as one success. Right? That would be a success, would be hitting the defective product. So yeah, so it'd be 5 choose 1 times 5, which is what I had. Population size minus k, yeah, 95. But that's maybe where I went wrong. Oh no, yeah, 95 choose little n is the number that we're choosing. This is saying with replacements. The probability of success changes on each draw. Yeah. No, this is fine. Yeah, we're sampling without replacement. Yeah. This is fine. Yeah. So I had it right. 100 choose 3 in the denominator. 5 choose 1 times 95 choose 2. I was off by a factor of 2. I did put it here, but yeah. I am moving today, Lola. But everything's basically packed and ready to go. And the rental truck is booked for 9, so I'm just waiting for my friends to pick me up for 8:30, and then we'll go to the rental place, and then I'll move. And yep. Yeah. I just figured may as well get a quick live stream in, because why not? Yeah. What time did I start today, actually? How do I find out? I guess I could just go to my YouTube. Well, that's all part of the learning process, Matthias. New backdrop reveal tomorrow. Yeah, I mean, notice the picture that's normally behind me is gone. Can I find out how long ago I started by clicking on this? Oh, nice. Yeah, there we go. Okay, 24 minutes. Okay, we're not gonna be here too much longer. I may as well use a little bit of time to um, do some work. I should. It'd be great. It'd be great to make some merch. I just need to like not be lazy and basically like drag and drop some compiled tech diagrams onto some t-shirts, and then we'll have hats. I'm thinking about a hat that has QP on it. That's one thing. There was a tree, huh? There was a tree on that picture, yeah. Yeah, tree 3. I think the moving's gonna go pretty easy, actually. Everything's pretty much packed up. I got a bunch of helping hands. Should be nice and smooth. Okay. I was thinking about talking about, root systems, but New Wave Infantry isn't here, who was asking about them yesterday. I guess I could still talk about it. What's the deal with root systems? I mean, the basic idea is this. We have a Lie algebra. We have a Lie algebra. Say G. Say over the complex numbers even. Although that notation normally means complexification, so I guess watch out. And we build from this a root system. So what is a root system? Basically, there's some joke here with Chow's moving lemma. Oh, yeah. Yeah. Well, we'll both think about it. Maybe tomorrow we'll come up with something. And it turns out you can decompose your Lie algebra. Well, this isn't what a root system is, but it turns out you can decompose your Lie algebra into some collection of eigenvectors. Hello, Femnal. Talking about Lie algebra stuff. Into some collection, basically indexed by functionals of what's called the Cartan subalgebra. So, for example, for GLN, this will decompose. This will just be your diagonal matrices, direct sum, all the non-diagonal matrices, and how should I index this? Like, this will be little eij, where eij will be the matrix that takes your diagonal matrix T1 to Tn and spits out the eigenvector Ti minus Tj. And so, of course, this will be the span of the matrix that has 1 in the ijth entry and 0 everywhere else. And so it turns out that this set, at least, it's basically like an abelian group, actually, of these special functionals. And if you tensor this up with the real numbers, you have a vector space structure, but it has a particularly nice structure. So in particular, it is closed under reflections. What are the other main things. I think this is like the big thing, one of the big things. Closed under reflections. You have a natural inner product. And it turns out that a bunch of numbers from this inner product. Well, I have to be careful. So it turns out that, what is it? So 2 alpha beta. So the circle brackets are the inner product here. Hi, Jens. This will always be an integer as well. So these are some of the key properties. So these things are actually what make it a root system. So a root system is really just any collection. It's just sort of any collection in the real numbers. Well, I'm abusing terminology between this, but maybe I'll call it R. It's just sort of any collection that basically has these properties. So it's some sort of also, by the way, it spans the entire space, something like this. And so there's an abstract notion of a root system, which is basically, just any assortment in Euclidean space like this. So, of course, I'd be remiss to not show you pictures. Root systems, not the one I'm looking for. So here are some examples of root systems. For example, these are all the 2-dimensional root systems that obey these properties. But how do we know that those are the only 2-dimensional root systems? We can see other root systems. And, Dynkin diagrams. That was the whole point of what I was getting to, right. That's where I was about to go anyways. So the point is, so we have a correspondence between Lie algebras and root systems. In fact, we can even go back and forth between these descriptions. But then the root systems as well, the key is, we've got this sort of finite number of nodes, and we have these sort of nice properties with respect to inner products. You have yet to make sense of tensor products aside from makes multilinear maps linear. Well, I have a mini series on tensor products. But of course, it's not quite directed at giving you a better intuitive understanding. It's more just trying to connect them to tensor products in physics. And I never finished that series. But maybe those videos will be helpful to you. And then, so our ultimate goal is to classify Lie algebras. And we realize that these are special cases of root systems, which are pretty combinatorial in some sense. And so we say, well, maybe it's easier to classify root systems. That's still not so clear. But what you can do is you can basically draw a graph where you take the roots. So, if we look at GL2, or let's make it SL2. Let's make it SL2. Not a big deal. So SL2, we get this decomposition. That's our diagonal matrices. Oh, sorry, I wrote that at the level of the Lie algebra, but it should be here. And then our other space is, well, it's the sum of these eigenspaces here, right? And so we have two roots, or I call it like E12 and E21, I guess. But in fact, E21 is the negative of this, right? So this would just be so here's a picture of a root system. So maybe I should have done SL3. It's slightly more interesting. Anywho, the point is, for each one of these roots, right? We've got these finitely many roots. Well, we can even divide up. So we can see that, up to scalar multiplication, I can cut sort of my set of roots in half. And this is kind of a general phenomenon here as well. You can basically split these into the upper triangular and lower triangular, or there's other ways of cutting it up. And then the rule is that basically you make a graph where you have a node for each of your, so you make some sort of arbitrary choice of positive versus negative roots. Actually, you want to include all the roots. So, but that is an important part of the story. No, wait. For the Dynkin diagram, you just want the simple roots. So I won't explain everything, but so you make an arbitrary choice of positive and negative, and then within the positive, you can make an even smaller choice that are called your simple roots that sort of generate all of the others. So in this case, we had one simple root. In the case of SL2, we have E12, E 1, 3, E, E 2, 3, and then we have the negatives of these, or you just switch these directions. But then E13 can actually be written as a sum of these two roots. So actually, for the SL3 case, here's an example of these would be our simple roots, right? They generate everything. And now what you do, so you write down all your simple roots, and I don't remember the exact number, but basically for this natural inner product that you have, you either draw an edge between them or you don't. Something like this, this vertex is not joined to this vertex. And sometimes you also draw, there are ones that look like this, and there's ones that can even have a double line. And these are how you draw the Dynkin diagrams. And the point is, the following. So we started with Lie algebras. We went over to root systems, and you can go over to Dynkin diagrams. So by that I mean, not only does a root system, you just write down these dots and vertices. If someone gives you a Dynkin diagram, by which I mean you've got these Dunkin' donut diagrams. You've got these vertices and edges between them. Well, you can read off from, so the vertices tell you basically what like a basis of your space should look like. And the edges tell you something about the inner product demands you have on the space, and that's enough information for you to go back and reconstruct and reconstruct a root system. And in turn, you can do that and reconstruct a Lie algebra. And now the point is, we want to understand what are called simple Lie algebras, right? We want to understand the simplest ones. And as you might imagine, this imposes an extra special property on root systems. So this is simple corresponds to irreducible root systems. And then in turn, the irreducible root systems, I think this just means that the Dynkin diagrams are connected, to be honest. And so if you want to classify all simple Lie algebras, at least over the complex numbers, then you just need to classify the connected Dynkin diagrams. And now this is a purely combinatorial thing. And now you can perform a purely combinatorial argument to find out that all of the root systems are of this form. And so, for example, yeah, so all the root systems are of this form. And so then once you've discovered all of the Lie algebras corresponding to these, then you know that you've found all the simple Lie algebras. So AN, BN, CN, and DN are all infinite families. AN basically comes from SLN. BN, CN, and DN, I always forget which one comes from which, but one of these is SO odd, one of these is SO even, and one of these is SP. And then finally, we have the so-called exceptional Lie algebras and their corresponding exceptional Lie groups. And these are just a finite collection of weirdos whose construction is, well, just less obvious, I suppose. Like, I think when we first discovered these, we discovered these via this classification of root systems through Dynkin diagrams, right? The other ones we knew we had these matrix realizations for, but it's not so clear a priori how do you realize E8 as some matrix, some system of matrices. And I think G2, for example, G2 does have a nice description. G2 is just the automorphism group of the octonions, BT dubs, I believe. I could be lying slightly. There might have to be some extra thing you have to do there, but yeah. Okay, it's 8:15. My friends are going to be here fairly soon. Time to move. Time to prove. Yeah. I'll find a collection of weirdos is a great band name. Yeah. Well, let's start working on songs, Boris. Let's start working on some songs. Okay, go prove some stuff.